I'll talk about how to look at the X matrix. So if you recall that we used to have this function for lasso regression in the R. I'm not going to specify in particular how to do this in R, but instead I'm going to tell you some general concepts so you can proceed to code it up. So if you want to estimate lasso model, you need at least two inputs. This is a matrix, and this is a vector, right? This vector dimension is n by 1, and your matrix n by k. N is a number of observations, and k is number of, let's call this independent variables. And this y represents the number, this n is number of observations, but y itself, this is our dependent variable. That's something that we're interested in. Okay, so this is a basic structure. Let me use an example. In our, let's use a very simple example. You want to regress the salary for one person on an intercept. Let's say this beta 0 plus beta 1, and this person's education. And maybe, let's say, this person's, let's say, his parents' education, let's say mother's education, and error term. So that's it. This is oversimplified model, and you can see this in many basic econometrics textbook. So what you have is for each observation, right? You have one variable. This is variable is actually beta 0 times 1, right? And this education, right? That's the one variables, and this is a scalar. This one is also scalar. They're all scalars. Okay. But you have many observations. So your I can equal to 1 to n. So the standard statistical software, such as R, it requires you to give all the data to them, right? Not just one observation. Those data are organized in vectors. So in this example, your vector Y will have a salary 1, salary 2 until salary n. That's all we have. And your matrix X include the first intercept's value, that will be 1, right? The intercept coefficient is beta 0, but the intercept is represent a constant 1. And you have the first person's education level and first person's mom's education. So that is 1, 1. That's the first row, and second row is another 1 because the intercept is always the same for everybody. And the second person's education level is 2, education 2. And his mom's education 2. And so on and so forth. And for the third person, it has an intercept value 1, education 3, mother's education 3, and so on and so forth. So you have altogether n observations, so that's n people. And the last one is the nth people's education and his or her mom's education. So as you can see, if you count number of rows, right, there's n rows. Each row represents one person, and you have 1, 2, 3 columns. So that's 3 variables. So this is this in statistics is called design matrix. In econometric, you see this very often as well, but it's okay. You just call this X matrix as long as the context is clear, right? So you have X that represents the collection of all the explanatory variable, including the intercept, and Y vector, that's the dependent variable that's you're interested in. So this is how it is. But in time series analysis, right, let me use a very simple example to show you. So your Y usually represents by T. That's time series, there's a time, right? So use T to represent subscript. Sometimes most of times, the explanatory variable, right, is not some other variable, but it's the lag of this particular variable itself. So for instance, your yt equal to, right, beta 0 plus beta 1 times yt minus 1 and plus an epsilon t. Now this is called our AR1 model, right? So anyone who has taken time series subjects or simple basic econometrics, you should at least have seen this step before. It's called autoregression, but auto means do it to itself. Regression is just regression, right? So your YT regress on a period before. That's basic structure. Okay. For this example, right, suppose in total our observations are y1, y2, everything's scalar, right, until y capital T. So you have a T observations. Now, if you want to feed this in a regression form to the statistical software that we have, it's a little bit tricky, because if you write y1 on the left-hand side, that'll be beta 0, right, plus beta 1. Now look at here, so you t minus 1, right? So instead, we should have y 0 and plus an epsilon 1. So this is one thing that you should do. But unfortunately, this is our data, right? Our data start from y1 and ends with yt. So in this AR1 process, right, this first observation is not directly doable. So what we do is we construct our y, from the second observation. Right? So we start with y2 equal to beta 0 plus beta 1, y1 plus epsilon 2. And so on, you will end to, you have y capital T equal to beta 0 plus beta 1, y capital T minus 1 plus T. Okay, so this is our general structure. So that is the value that we're going to need. Right? Let me copy this and go to next page. Right, let's leave it here. So now you see what's in this particular regression, we're going to form our vector of y's, which will be, or y will be, right, y2 until y capital T. And our X matrix, okay, how many variables do we have? We have an intercept right here. We have a leg 1, so we have 1 and 2 independent variables. So the first column will be 1, 1 until 1. So this is our intercept. The coefficient is beta 0. The second column is y1 until yt minus 1. So our x is t minus 1 by 2. So the number of observations in the regression is not t, but t minus 1. Simply because there's a lag structure, so you cannot put y1 in the y matrix because you do not observe y0. This is here. You cannot include this one because this one is not observed. Okay, you have to start from the point that the data become available. Right. So in this y is counting from 2 to t, so there's also t minus 1 times 1 vector. So this is the y vector. So you see, if you have 1 period lag in the regression, your data effective number of observation will be reduced by 1. So similarly, right, if your model is AR2, that's autoregressive of order 2, right, yt equal to beta 0 plus beta 1, yt minus 1 plus beta 2, yt minus 2 plus epsilon t, right? And your observation start from y1 to y capital T. You want to do y1, but that is not possible because you do not observe y0, you do not observe y minus 1, right? So these two observations are not, they don't exist. And if you do y2, you have y beta 0, beta 1, y1, this is okay, but right, the second leg, that's y0, this one doesn't exist. So the data becomes available when you start from y3. So that is beta 0 plus beta 1 y2 plus beta 2 y1 plus. And therefore, you lose 2 effective number of observations for order of 2. And your first observation should start from the third observation. So think about if you have an autoregressive model of, let's say 240, right? So you need many lags. So your first observation, right? In the previous one, you have AR1, your first observation should be Y2. You have AR2, your first observation should be Y3. So you have AR240, your first observation should be Y241. That'll be your beta 0 plus beta 1, Y240, right? Plus until your beta, right? 240 times Y1 plus epsilon t. So this are 240 terms. And then if you want to construct your y vector, you start from y241 until y capital T. That's your y vector. And your x matrix will start. There's a 1, right? And there's a y240, so on and so forth, y1. But for the second observation, that's 242. That's the intercept is always 0, but this 241 until y2, and so on and so forth. For the last observation, you have yt minus 1 until yt minus 240. So that's the idea of how to construct the X, or let's call this design matrix, when the time series model includes the lags. You have to discard the first chunk of data, because the right-hand side, there's no corresponding value. You have to find a starting point such that all the values are observed. Then you do the regression.